University. The topic of my title is Structural, Morphological, Dielectric and Conducting Properties of Zinc Oxide Nanoparticles. First, I want to let me give you some introduction and the significance of zinc oxide nanoparticles. So usually, the zinc oxide nanoparticles are inexpensive, simple to synthesize, convenient, non-toxic, biodegradable, non-volatile, and yes, stable hexagonal wood-side structure in which the zinc and the oxygen atoms have highly ionic bonding in nature. They possess a direct wide band gap, that is a type of semiconductor within the range of 3.3 electron volt. Large free exciton binding energy approximately 6 milli electron volt. Good transparency, high electron mobility, and a high thermal and mechanical stability at room temperature, a broad range of radiation absorption, and a high photon stability. So, because of these significant characteristics, they are very useful in different kind of applications. It also contains large voids, and hence the addition of impurities to zinc oxide lattice often induces the dramatic changes in the physical and optical properties. Thus, it is possible to tune the band gap of the zinc oxide by either varying the chemical composition, such as doping or alloying, or quantum confinement on the nanometer scale. The dielectric permittivity and alternate conductive current conductivity properties are attributed to interfacial and orientation polarization and the presence of more charge carriers respectively. When doping or alloying with other metals or materials, these properties can be increased or decreased significantly. In addition, upon changing the size of the zinc oxide nanoparticles, the dielectric constants can be increased or decreased. The value of dielectric loss at low frequencies usually observed, which can be attributed to the presence of impurities or the crystal defects present in the zinc oxide nanoparticles. So, to date, several methods are available, such as hydrothermal, solvothermal, co-precipitation, solar chemicals, soil gel, microemulsion, chemical vapor, thermal decomposition, microwave radiation, laser ablation, etc. have been employed to prepare such kind of zinc oxide nanoparticles. The main aim of this work is to investigate the electrical properties of zinc oxide nanoparticles calcined at 500 degrees Celsius. Because when we try calcinated at a different kind of nanoparticles,
sorry to interrupt you, sir.
Yeah.
Your slide is not changing.
Hello, madam. Excuse you.
Your slide is not changing.
Yeah. Now changing, madam. It's okay.
No, you should click on the slide number, second, third, whatever you presenting.
Yeah, here. Can you see the figure now, madam?
Only first slide is in here.
Yeah, second.
No, you should click on the slide from your side.
No, madam.
No.
The slides can move actually now from my side. I can.
Yes, now it is changing.
Oh, okay. Well, how about see now, madam? Now can you see the second slide?
Yes, yes.
This synthesis of zinc oxide by co-precipitation method.
No, it is third slide.
Third slide, yes. Yeah, okay. So usually the synthesis of synthesis of zinc oxide nanoparticles can be prepared by co-precipitation method. Usually the zinc nitrate, deionized water solution of zinc nitrate with KOH is placed in the beaker and stirred under the magnetic stirrer for several minutes, and then during that following the reaction, we will get the white state of the zinc hydroxide precipitates. after the centrifugation, you will get the after 30 minutes you will get the white precipitate of zinc hydroxide nanoparticle. The resulting particles was filtered and tried at room temperature, and then finally washed with water and methanol, and the resulting sample was calcinated at 500 degrees Celsius in the furnace at 500 degrees Celsius. You will get the a dry sample of zinc oxide nanoparticles. So after cooling to the room temperature, the resulting zinc oxide nanoparticles was used to characterize and investigate different application properties. This slide shows the IR spectrum of zinc oxide nanoparticles. Here you can see that the peaks appear at 3,400. 27 and 14 corresponds to the stretching vibration of the water molecules, and 1,597 and this also corresponds to the stretching vibration of water molecules. This would be present during the preparation of the pellet preparation actually. So the peaks observed at 1,384 and 3,052 nanometer, per centimeter, are due to the presence of the methanol that could be present during the washing of the nanoparticles. So the zinc oxide nanoparticles was finally confirmed by the appearance of the peaks appeared at around 558 per centimeter. So after confirming this nanoparticle through IR spectrum, we want to use the another method, which is called the X-ray diffraction method. Here we can see the zinc oxide shows the different kind of Miller indices. We can see they were indexed in the red color, that is the standard one. When we compare with the standard value of this zinc oxide with our prepared synthesized zinc oxide, you can see that in the table, the lattice constant value A, B, C, which is they are almost close to each other. By using this lattice parameter, the hexagonal, that is equation 1 by d squared HKL is equal to 4 by 3 H squared plus HK plus A squared by A squared plus L squared by C squared. By using this one, you will get the lattice constant for these nanoparticles. Apart from that, you can see the angles also. You can see by using this for each Miller indices. When you compare the standard diffraction angles, you can see the experimentally observed zinc oxide nanoparticle also very close to each other. So apart from that, we wanted to check out the crystalline diameter, and using the equation, d by Scherrer equation, that is d is equal to k lambda by beta HKL cos theta. So from this equation, you can find out the diameter size of the crystalline size, which is almost here 535.6 Armstrong meter. And with the lattice strain, there is a 3.17 or 3.71 10 power minus 3, which is also close to the theoretical value. Apart from that, we want, by using the particle analyzer, we want to make sure that the zinc oxide is formed as nanoparticle or not. And from this analysis, you can see that the zinc oxide nanoparticles are found in the range of nearly here nearly 70 to 120 nanometer range. Here you can see both the size distribution from the histogram and the intensity value. In addition, we want to confirm the elemental analysis of elemental composition of zinc oxide nanoparticles. We performed X-ray photoelectron spectroscopy also. Here you can see that the presence of zinc and oxygen in this and the binding energies nearly 1,000 and 500 electron volt respectively. In the right hand spectrum, you can see the clearly the ZP, that is 3 by 2, that is 1 by 2 orbital of the range, the binding energy. And then for oxygen also, you can see that here, there is two kind of peak appeared here. One is comes from the oxygen and another one comes from the moisture, water moisture molecules also. So apart from that, we wanted to check the SEM analysis. From the SEM experiment, we can observe that the densely packed arrangement of particles with a spherical morphology. That is van der Waals interactions of the small interaction takes place within the small molecules, and the besides the magnetic interaction are caused the existence of larger nanoparticles. So we can see it clearly. Besides, we see through the EDX data, we can find out the ratio of the zinc and oxygen molecules. And the results show that it's 1:1 binding on 1:1 ratio from the oxygen and the zinc. Here you can see the small percentage of carbon, which is obtained from the carbon debt, which is used for doing the experiments. And the next one shows the UV visible absorption spectrum of zinc oxide nanoparticles. Here you can see the absorption spectrum below the 400 nanometer corresponds to the electronic transition between zinc and the oxygen bonding interactions. So from this absorption, we can find out the energy gap between bonding gap. The bonding gap of the zinc oxide nanoparticles by using the top plot. That is AH nu n is equal to KHV, that is EG. There is A is the absorption coefficient, and the H nu is the instant photon energy, and the K is the constant, and so the EG is the energy gap. By using this equation, we can find out the band gap energy is 3.16 electron volt. So, after characterizing this zinc oxide nanoparticle, we wanted to check out the application of this zinc oxide nanoparticles. In this, when performing the dielectric measurement, we can see that the plot of dielectric constant versus the frequency as a function of different temperature, as shown in this figure. Here you can see that at high frequencies, the dipoles, it shows the maximum dielectric constants around the 98. So at the high frequencies, the dipoles may struggle to reorient quickly enough to match with the changing the applied electric field. So you can see there is a suddenly the drop in the dielectric constant until higher frequencies. Whereas at the high frequencies, you can see the dielectric constant almost 98 because of the quick response of the dipoles against the applied dielectric field. In the case of dielectric loss, that is the right-hand figure, you can see that the dielectric constant becomes large at lower frequency, which is nearly 0.98 also. Okay, so this one reaching to at nearly 10^3 hertz, because the sluggish response of orientation of the molecules towards the applied electric field, and the contribution of charge accumulation at the interfacial of the nanoparticles. So it gives the dielectric loss is high at the low frequencies. Whereas in the case of at high frequencies, the dipole moments of the dipole are within the zinc oxide nanoparticle experience difficulty keeping pace with the rapid change in the direction of applied field. So the resulting, this results in reduced capacity for energy dissipation in the form of energy loss at the high frequencies. The next slide shows the conductivity of zinc oxide. Here you can see that the maximum conductivity observed at 3.5 × 10⁶ Siemens per centimeter. At low frequencies, you can see that there is from 10⁻³ feasible conductivity was attributed to the formation of less conducting grain boundaries due to the small number of charge carriers tunneled through the potential barrier. Whereas at the high frequencies, an increment in the conductivity was observed due to the large number of charge carriers that can overcome the potential barriers. That's why we get the high conductivity at a larger frequency. This table shows the comparison chart of different properties of zinc oxide nanoparticle synthesis by precipitation method. So here you can see the earlier reports shows the zinc oxide nanoparticles calcinated from 150 to 900 degrees Celsius. And some of the report didn't show the dielectric and the conducting property, but only 3-4 papers only they reported about the dielectric and the conducting properties, which are lies in the range of 10⁻⁵. But in these studies, they can,
sir, please wind up in given time and come to conclusion.
Now I am going to conclude now. So this is my last conclusion. So zinc oxide nanoparticle synthesis by simple co-precipitation method. The obtained samples were characterized by FTIR, products, or UV visual spectral techniques. The UV visual absorption spectrum zinc oxide nanoparticle sodium and showed an optical band gap of 3.16 electron volt. From the impedance spectroscopy, the zinc oxide nanoparticle showed the dielectric constant approximately 90, not 50 here, sorry. 90 with almost dielectric constant of 0.9 at the high frequencies owing to field rotation polarization and the space charge. Both the dielectric and dielectric loss of zinc oxide nanoparticle indicated decreased behavior and with frequency due to formation of boundaries between the nanoparticles. It also showed the alternating current conductivity of 10⁻⁶ Siemens per centimeter, which is slightly increasing at variable applied frequencies, indicating that the presence of more charge carriers are contributing to conducting process. These important findings make it an interesting material for potential use in lower frequency devices such as UV photodetector, optoelectronics, and spectronics. So finally, I would like to thank my PhD scholars, Anurag Yadav, Silu Nayak, Swati, and MSc student Ajivas Vakshan. I also would like to thank the funding support from the in the form of non-native Pandey University Fellowship and the Central University Instrumentation Facility of Pandey University for providing the such kind of experimental studies. Thank you for your kind attention. If you have any question, please.
Thank you, sir. Nice presentation.
Thank you.
Now the presentation is open for the discussion. If anyone have any question. Okay, I have one question for you.
Please, madam.
What is the dielectric loss of Z?
Hello everyone, myself is Dr. Vinay, and I'm working as a professor at Savita Medical College and Hospital. And the topic of my presentation is promising lignin nanofiber-based material for environmental applications. So before starting, I would like to tell you about why the lignin is more important and promising candidate nowadays. For the last decade, it had been observed that the lignin is coming in many of the environmental applications as well as in the medical applications as well. And there are several reasons for that because it's easily available and it has low cost. And another thing is that we can easily extract it from the lignocellulosic biomass. So if you talk about the lignin origin, so mainly for those who are working already on the biomass and lignocellulose materials, they know that the cellulose is that lignin is mostly extracted from the lignocellulosic biomass, maybe wood, pulp, or bark. And three major components that are present in the wood biomass, and we call it biomass simply or lignocellulose biomass as well. These are cellulose, hemicellulose, and lignin. Although all of these three components have their individual identity and application. For example, cellulose can be converted to nanocellulose and other materials like we have carboxymethyl cellulose, which can be converted to other value-added products like we have ethanol, FDCA, lactic acid, and sulfur. All of these, like we have sulfural and lactic acid, these are the platform products for manufacturing and synthesis of the other byproducts and also useful materials. Some can be used for the as a fuels also, and they can be converted to some of the polymers as well. Another aspect that lignosulfate, or we can say lignin mainly, that can be converted to some of the useful products, like we have a bioplastic, and if it's environmental application, they can go for energy storage, carbon fibers, carbon nanofibers, or lignin nanofibers with the bacteria to produce the bio. If you talk about the lignin application, lignin used in, I told you that the materials that lignin nanofibers, nanoparticles, and they can be decorated and surface coated with a different functional group for use in a different material applications. They can be used in energy, UV blockers, and the pulp and paper, and agriculture and other environmental applications. So lignin can be functionalized. We can add the functional group, and recently it had come up with a new application, like a new material. We call it hydrogel. So hydrogels mainly they have different desired properties, that they are sustainable, and they can absorb more of the environment pollutants, and they can be also used for the purification of the pollutants in the air. Another thing, they can also be used in catalyst and photocatalysis, and they can be used for the porous carbon nanomaterials, and they can be used for the composites and blends, and we can make nowadays biofilm also, films also, film membrane. Then, if you talk about the lignin, because lignin from the lignocellulosic biomass doesn't extract easily. So we have different processes for lignin processing. These include polymer bending, extraction, then purification, etc. And if we have to make the lignin nanofibers, we need to go for the spinning. That can have different methods like wet, dry, gel, and melt spinning. After spinning or making the nanofibers, we need to go for the stabilization, which can be used like chemical or thermal stabilization. The next step is a carbonization, where we treat the surface of the fiber and also activate some of the functional desired groups that can be used. For example, if you're going for the dye degradation, we need to search for the corresponding modification. At the same time, if you are going for some of the pollutant degradation, like we have endocrine disruptors or cancer-causing chemicals like phthalate, etc., which are present in the water. So we can go for the water purification as well, wastewater treatment, and we can go for the effluent treatment from the we can say ladder in the. If we talk about the nanofibers, or we can say lignin nanofibers, so because for the last decade, it has been known how we can prepare the nanofibers using the different materials, like we have chitosan, we have a biodegradable material like chitosan, alginate, gelatin, all these. These methods are known. But here, so if you talk about the general method, what happens there is a highly charged, high voltage syringe is there, where we inject our material, and this material is released from the nozzle in a in a vacuum chamber, where a rotating drum is there, and due to highly charged material here, it goes to roll over the drum, and this drum collector, it rolls like a reel, like with spin the thread, and after that we get a sufficient amount of that thread, and that we can later use, and we can characterize it. So to do that, we need to also stabilize the processes like thermo stabilization, carbonization, how much carbon content we need. So based on that, we can maintain the temperature, or as well as at the rate of degree of the increase in the temperature. Next thing is that what are the property changes that we can do in a lignin nanofiber, and how it is going to affect your properties as well as the application part. So, for example, this is one of the research paper. There are some data I'm going to present here. So, this is sugarcane bagasse. Bagasse, for those who don't generally obtained from the sugarcane waste material after extracting the juice. So here you can see this is the untreated bagasse that has some size and thickness and consistency. And here what they did, they have treated it with the ionic liquid. So after treating the ionic liquid, this is the B sample B. And third is a nanofiber bagasse. They have made nanofibers and they find size. And the fourth one, they have used ionic liquid also here and they made it nanofibers also. So what happened, you can see here in the scanning electron microscopy result that this is natural bagasse without any treatment. That's the control bagasse. As compared to this, here you can see after treating with the controlled ionic liquid, although we can see there is some changes in the structure, but that are not, we can't say that the more of the surface area have been increased. But if we go to the C, this is the nanofibers, and we can see here that the properties that the pore area at the same time the surface area have been increased. And in the case of both where we have used ionic liquid also and also that we have made a nanofibers, the we can say porosity and more of the surface area has exposed. So we can see that on the treatment and the method also depends on how we are going to increase your material more reactive. So if you talk about the mechanical properties, here we can see like this, we have a tensile strength here, modulus. So we can see as compared to the control bagasse, after the tensile toughness, tensile modulus, and also tensile strength have been changed. In most of the cases, it's going to increase. You can see that after treatment, so major purpose of making the lignin nanofiber and not using the raw lignin is that because after making the nanostructure, the porosity and the functional group and surface area is increased. And mainly that is used to enhance the property to bind our target pollutant. If it's a dye-degradation, then methyl orange or something, or if we are going to purify some of the phthalate esters that are causing cancer, that you can do textile pollutants, effluent. So it enhances that property. At the same time, if you are talking about medical application, what happens in that for the medical material, it should have a higher binding property and absorb over a time. So that we call as the controlled drug release. So as spinning, so one more method, this is actually quite recent method here that we can use. They have, when somebody has used for producing the lignin nanofibers. Here, what we do in place of the air spinning, we do it in some liquid. That's why we call it a wet spinning. And this is actually with a similar process we use in our laboratory to make the hydrogels, and we can say to make the hydrogel beads. What happens, these polymers materials like we have chitosan, we have alginate, we have this gelatin, any of these polymers, when we drop them in a very highly alkaline solution like say normal or 5 normal anode, when they go inside the solution, immediately they will due to hydrophobic interaction, they make some solid structures that we call the beads. So method can be used to prepare the nanofibers. In that, what we do, we make a calcium chloride, and then our solution. So it can be it's a very less concentrated millimole or something. And when we release the lignin and solution, it takes some level 5. Here we can see ligno. This is a lignocellulosic will only here alginate also. So you can see after the quality and the structure have been increased. So because actually lignin itself is not much stable, and you can see here the brown color, because when we add in water, it starts dissolving and it gives a very dark color like Coca-Cola. So that is undesirable property. So that we have to add some of any of the we can say polymers like chitosan or something that they have used. Another method to improve the efficacy of materials, like we have carbon nanofibers, we use the hydrothermal treatment. In the hydrothermal treatment, we prepare the nanofiber material using nanofibers and heat them at a very high temperature, like you can say 400 to 900 degrees Celsius, 2 to 3 hours, depending on the what pore size and consistency we need. So we can see here after the treatment with the react the so
So you are not audible.
if I can you hear now? Hello.
Yes, yes, sir.
Ma'am, can you hear now?
Yes, yes.
Okay. So if we talk about the major challenges, so challenges, first challenge is that the lignin is not a stable compound. If you are going to increase the pH of the, if you are going to dissolve or solubilize the lignin in water, initially it will be soluble until a pH of 8. But if you increase the pH less than 8, it will start getting more turbid, like a curd-like structure. And if you reach the pH of 2, it become like a soil or sandy structure. And it become like it lost the consistency of the liquid. So that's why its stability is also is one of the problem that we have to understand. And another problem is that because this material is not much stable, so upscale also we need to understand. Next is the injectability. We can see that it's injectable and we can make the nanofibers. It still it requires some of the optimization. And stability, I already talk about that. So actually, this is one of the my previous work where we tried to use the black liquor from the pulp and paper mill industry, and we dried it, and that we extracted the bioplastic that we tried to produce PHA from it, and successfully we got some of the dried PHA that we have characterized. But if you talk about the yield, that was very quite low. We can say 3 gram per liter. So so we can't say that the maximum yield was around 12 gram per liter. So this we cannot upscale. So upscaling is a challenge, and it's difficult to optimize these processes. So optimization and scale up is the major challenge when we are going to use lignin. Otherwise, lignin is a very cost-effective material and easily available. It can be used, and we can say it's in because already polymers are in the on the way to for the environmental degradation and remediation strategies. But lignin is, I think, it will take some time to go forward. So that.
Good afternoon, sir, and good afternoon, everyone. Today, my name is Jaspreet Kaur from Punjab University, Chandigarh. I'm pursuing my PhD, and the title of my presentation is Intra-particle diffusion model to explain the adsorption activity of ammonium vanadate nanostructures. So these are some outlines of this presentation. The first, we introduce the objective of this presentation. After that, the material and the methods. And in result and discussion, we will focus on the characterization, different adsorption kinetic models, and their what's the rate constant play an important role in these kinetic models, and understand the difference between shaking and the stirring. And for this, we will also introduce the intra-particle diffusion model, and then conclusion and references. So these are some objectives of this presentation. As we can see, the textile industry plays an important role in our daily life. But because of the water pollution, it's necessity of today to control this water pollution. So scientists have a lot of work have to be done on these problems, and to control this problem, different methods have to be applied. For example, filtration, membrane separation, adsorption, and photocatalysis, and so on. Among these different methods, dye adsorption is an important and large scale method, and we can apply this method on a large scale. So during the adsorption, it's become important to understand the concept of the technique that we have to be applied for the adsorption, whether we go it on through a shaker or on a stirrer, because these mechanical instruments also influence the adsorption activity. So for that, to understand these two different mixing techniques, the intra-particle diffusion model helps to understand the concept of the adsorption activity. So the next one is the materials and method. The nanostructures that I have chosen for these technique is ammonium metavanadate nanostructures, and these have been synthesized by using the Solgel method. And further, the adsorption activity have been analyzed by different kinetic models. And before going on the kinetic models, we first we calculate the removal percentage that the material have to be shown, and after that different kinetic models have to be applied. The first one is the pseudo second model, pseudo first order model. The second one is the pseudo second order model, and after that the IPD model have to be applied. These are the characterization results. Among the characterization that I have done is XRD, FSM, and SRTM.
Please go ahead, sorry.
In XRD, we have analyzed the structure of the material, the diffraction peaks that presented here, 10.8, 17.6, that correspond to the different planes of these nanostructures that will confirm the structure that have to be synthesized. And after that, the FSM and SRTM, these results represents the morphology of the nanostructures. As we can see, in HRTM, the nano ribbon type structures have to be predicted, and these nano ribbons are self-assembled to form the nest-like nanostructures. And these nest-like nanostructures show the porous character of the material that will help to absorb the dye materials on the dye molecules on the adsorbent material. The adsorption activity that have been analyzed by two different mechanical instruments. First one is shaker and second one is on stirrer. The difference, as we can see in the removal efficiency, that the stirrer will absorb the dye molecules. Approximately 99% dye have to be absorbed within 10 to 15 minutes. On the other hand, in a shaker, it will take about 50 to 60 minutes. So there is a huge difference in the dye absorption process during the dye absorption. And these are the fixed parameters that I have applied for this process. The adsorbent material that I have taken, dye concentration, total volume of the solution, and what's the speed of the stirrer and the shaker I have fixed, and on which I have performed the work. So we can see here's the difference between the shaker and the stirrer process, and then this difference have to be calculated, or we can say analyzed through different kinetic model as well. So the kinetic model that already I have discussed, the pseudo first order and second order model have to be applied. From them, the pseudo second model order model show the best fitting. So that's why I have only presented here the pseudo second order model. And this is the pseudo second order model for the shaker, and this is for the stirrer at different concentrations. And these are the results that I have shown here. What I have to be present here, or what's the purpose to present here the pseudo second order model, that about the rate constant. As we can see, the rate constant K2 for shaker is 0.0024, or on the other hand, for the stirrer, it is 0.065. So that means for the stirrer, the rate constant actually tells about the affinity of the adsorption. So in case of stirrer, its value is higher as comparison to shaker. So that means in the stirrer, the dye materials are more effectively or more fastly adsorbed on the adsorbent material. The interpretation of these results also have been done by the intra-particle diffusion model. Intra-particle diffusion model that I have presented here for the stirrer and the shaker, and the result also presented here. Again, here the K1 and K2 value, these are the different layers of the adsorption, because in case of intraparticle diffusion model, three type of the layers phenomena have to be take place. The first layer is the mass adsorption, second one is the intraparticle diffusion, and the third one is the surface adsorption. So as we can again see in the shaker, the K1 value is lower as comparison to the magnetic stirrer, the K1 value is greater. So again, we can say the shaker have more affinity, or we can say this mechanical instrument have more ability to absorb the dye molecules on the adsorbent material. So this is the conclusion of the whole discussion. The first one, the synthesis of the nanostructures. Second one, the fitting on different adsorbent model, kinetic model, so the first order and the second order. And to predict about the rate constant for the stirring is more, or we can say greater than as comparison to the shaker. And further, the evaluation of the process of mixing have been done by using the inter-particle diffusion model. And three type of the layer that I have discussed, the initial surface adsorption, intra-particle diffusion, and the equilibrium state. And the rate constant K1, K2, K3 of these layers have been discussed. And of course, the K1 is greater for the stirrer as comparison to shaker. So we can say the stirrer show more ability for the adsorption of the dye as comparison to shaker. So these are some references. So thank you so much.
Okay, thank you.
Good afternoon, everyone. Respected to you all. The topic which I'll be presenting today is evaluation of the new activated carbon and graphene oxide as an efficient composite adsorbent for the removal of herbicide 2,4-dichlorophenoxyacetic acid, composite synthesis, characterization, and adsorption. My name is Imotila T Longchar, and I am a research scholar from the Department of Chemistry, Netherlands University. First of all, we know that water is the basic necessity for the sustenance of life on Earth. However, with tremendous increase in numerous emerging contaminants, water is being polluted every day, and it disrupts the life cycle of not just aquatic ecosystems, but also our life. In fact, it has been reported that more than 2 million tons of wastewater a day is discharged into the global ecosystem. Now, one of such waste is a herbicide that is 2,4-dichlorophenoxyacetic acid. This herbicide is commonly used by agriculturalists and farmers because it is cost-effective and has wide applicability. This herbicide disrupts the waterways because it is slow in biodegradability. Also, long-term consumption of this herbicide in humans can cause carcinogenic properties. It also damages vital organs like the liver, kidneys, and central nervous system. It also disrupts the life cycle of aquatic ecosystems. Hence, removal of this herbicide from water is crucial. In our study, we carried out a particular water purification technique, that is adsorption, for the removal of this herbicide from water. In adsorption technique, what happens is that we make use of an adsorbent such that the pollutant gets accumulated on the surface of the adsorbent and is being removed from the waterways. Now, in order to carry on with the adsorption technique, selection of an adsorbent is very necessary. In our study, we used two different adsorbents such that it is combined together to form a composite adsorbent, and that adsorbent is used for the removal of the herbicide from water. Activated carbon is a carbon-based substance and is used as a good adsorbent because it has large surface area, well-developed pores, its production cost is low, and it is easy to regenerate. Graphene oxide is also a carbon-based adsorbent, and it is a single atomic layered material. Graphene oxide is highly economical, it has abundant functional groups and imperishable hydrophilicity. So these two adsorbents are combined together to form a composite with enhanced properties, like it has abundant functionalized groups, increased surface area, and decreased agglomeration of the graphene oxide because graphene oxide is a layered material. Hence, when combined with activated carbon, its agglomeration decreases. Also, the composite can have higher adsorption capacity. So to understand more about the activated carbon and graphene oxide composite, let us dive into the preparation of the activated carbon and graphene oxide. First, the two adsorbents are prepared separately. Activated carbon can be obtained both commercially as well as it is prepared in laboratory. In our case, we make use of a bio-waste material such that the carbon produced is low cost as well as eco-friendly. Thysanolena maxima biomass, which is commonly known as tiger grass, is used for the preparation of activated carbon in this study. This biomass undergoes different carbonization and activation using activating agent potassium hydroxide at particular temperature to obtain the final product, that is activated carbon. Graphene oxide is prepared using modified Hammer's method technique, where the starting precursor is the graphite powder mixed with different reagents, and at particular temperature and time we obtain graphene oxide. To synthesize the activated carbon and graphene oxide composite in the ratio of 1:2, we disperse the two adsorbents in a sonicator, after which it is transferred to a magnetic stirrer, filtered and dried to obtain the final composite, that is activated carbon and graphene oxide. Now, to know whether the composite that has been prepared is formed or not, we undergo different characterization techniques. The first graph shows the XRD spectra of the composite. From here, we see that there is a peak at around 11 degrees, which corresponds to the plane 200, which shows the peak of graphene oxide. Also, two other peaks at 2 theta is equal to 26 degrees and 42 degrees, corresponding to the planes 002 and 100, corresponds to the activated carbon peak. From here, we see both the peaks of graphene oxide and activated carbon, which can confirm that the composite of activated carbon and graphene oxide has been formed. The next spectra shows the FTIR spectra of the composite, which shows the surface functional groups of the composite. From here, we see that there's different functional groups present at different peaks, like OH functional groups, CH functional groups, carbon double bond oxygen functional groups, epoxy groups, etc. From figure C, we see the N2 adsorption-desorption isotherm. From the figure, we can analyze that the composite consists of a mesoporous system. We also undergo bed analysis, from where we can see that the bed surface area of this composite has been determined to be 958 meters square per gram. The average pore diameter has been determined to be 2.65 nanometer, and total pore volume is 6.37 centimeter cube per gram. Figure D shows the same image of the composite. From the figure, we see rough and uneven surface. Also, we see deep and well-defined pores with different shapes and sizes. Figure E shows the EDX analysis of the composite. We see two elements present, that is carbon and oxygen, and its atomic percentage and weight percentage is as shown respectively. Figure F shows the TEM image of the activated carbon graphene oxide composite. The sheet-like morphology with variation in transparency shows the structure of the graphene oxide. Spherical dots that are scattered on the surface of graphene oxide shows the structure of activated carbon. After the characterization, we move on to the experimental section, that is adsorption equilibrium experiments. 5 different parameters were considered in order to analyze the removal percentage and adsorption capacity of the herbicide pollutant. The different parameters considered were activated carbon graphene oxide dosage, concentration, contact time, pH, and temperature. At an optimum value, after undergoing different experiments, we see that a dosage of 0.1 gram per liter, the pollutant concentration of 150 mg per liter, contact time of 120 minutes, maintaining pH of 2 and temperature of 298 Kelvin, highest removal of 96% of the pollutant using the adsorbent composite was seen. The maximum adsorption capacity was also seen at 71.95 mg per liter. This adsorbent is also experimented for regeneration and reuse for 5 different cycles, where we see that even up to the 5th cycle, removal of almost 79% was seen. From here, we can conclude that the adsorbent can be regenerated as well as reused for a couple of times. So in order to conclude, we see that activated carbon and graphene oxide composite has been formed and is used for the removal of herbicide 2,4-dichlorophenoxyacetic acid from water. The composite has shown a surface area of 958.569 meters square per gram. At optimum values of dosage 0.1 gram per liter, concentration of 150 mg per liter, time of 120 minutes, pH of 2 and temperature of 298 Kelvin, the highest removal of 96% was seen. Also, the adsorbent shows easy regeneration and reusability. These are some of the references that were used. Thank you for your patient listening.
First of all, thank you for this opportunity. My name is Kumar Pandey. My topic is Superionic phase Na2M004. My name is Kumar Pandey. My supervisor, Dr. K.M. Misra. My introduction. Superionic conductor represent a class of material with exceptional potential for advancing solid-state battery technology and under electrochemical application. Sodium molybdate Na2M04 has emerged as a promising candidate in this domain due to its intrinsic crystal structure and high ionic conductivity properties. Second, this paper explored the ion transport mechanism, separation of ionic and electronic conductivity, thermoelectric power, and application of Na2M04 as a superionic conductor. The crystal structure of Na2M04, characterized by its layer arrangement of sodium and molybdate ions, facilitated facile ion migration pathways. Ionic conductivity measurement reveal a significant enhancement in Na2M04 at elevated temperature, indicating its suitability for practical application requiring a high ion mobility. Material preparation experimental technique. Na2M stated 99.9 purity, procured through MS Rare and Research Chemical Bombay, Indian molybdenum oxide MO3 with stated purity 99.9 purity, procured through MS Champura, Calcutta, India. No specific chemical impurity have been given by the supplier. Starting material was divided into equal portion based on the molecular weight, carefully mixed. Firing temperature 740 Kelvin on the solidified melt. Electrical conductivity was measured for this self-made sample holder. It is composed for a test tube with flat bottom made by corning glass and two parallel plate silver electrodes that are the same size, have the same surface area. Two substantial silver cables are used to link these two electrodes to the outside world. A sample container is filled with the substance whose conductivity has to be determined, then pressed. Then it is cooled until the salt within dissolves. It cools to room temperature gradually. The measurement device is then linked to the outside electrodes. Using the sample container method described elsewhere, the measurement of conductivity were carried out. Na2 produced in various batches have their thermoelectric power and electrical conductivity related a temperature function. The instruments were taken through the heating and cooling cycle separately. No considerable variation has been studied in thermoelectric power, electrical conductivity value, then cooling and heating cycle. The finding has been the figure of log sigma T versus temperature, and this is thermoelectric power versus temperature. Thermoelectric power versus temperature. Curve ion and electron migration, or perhaps both, contribute to electrical conductivity. Dielectronic contribution have quite distinct underlined hypothesis. Therefore, it is necessary to determine here is so that electrical conductivity and ionic conductivity separation from total conductivity. This is the thermoelectric power from versus temperature, and this is electrical conductivity versus temperature. Therefore, it is necessary to determine whether the conductivity is primarily ionic or electronic in order to give any relevant discussion of electrical conduction. There are standard ways to this, but measuring DC electrical conductivity at time function using electrode that inhibits ionic but not the electronic conduction is a far simpler technique. Here my graph of conductivity versus time, and this is the graph of conductivity versus temperature and thermoelectric power versus temperature. This is the graph of conductivity ratio of ionic and electronic conductivity of is equal to R versus time temperature. This is the graph of conductivity versus frequency. If the electrode being used to test the conductivity are able to stop the flow of ions, a time-dependent diselectrical conductivity will often be seen in the solid with ionic conduction. Positive ions flow in the field direction, where negative ions move in the reverse direction at the time when the electric field has been applied to the electrodes using a potential difference. Ion cannot discharge at the electrode because electrodes are impeding their passage. Therefore, they start to accommodate the state. Thus, as more as ions are unable to reach the electrode and the DC source of current falls, the net force exerted on the ions seeking the flow in that direction diminishes. Over time, the opposite field tend to rise and eventually catch up to the applied field. tend to time tends to infinity. Therefore, the DC current in pure ionic solid decline with time and eventually tends to zero. If the approximation argument is applied to the example of mixed ionic conductor, one would anticipate a steady drop in the current that would eventually tend to reach a constant value. This current develops because the polarization caused by the ions prevent the electric field from being zero. When this transit has passed, the remaining constant amount of current may be completely attributed to the electron. The transit is caused by ionic charges. The entire current produced by both ions and electrons is known as initial current. Thus, we may assess the overall conductivity as well as the ionic electronic component from time-dependent current measurement at low but constant temperature and electric field which were conducted to from plot. This is the graph of conductivity versus time. This is the graph of at lower temperature, the tendency of consistency takes a little while the emerge, but it becomes stronger to the as the temperature rises. This is the table of the ionic total conductivity, electronic conductivity, ionic conductivity, ratio of ionic electronic conductivity, and this is the different temperatures. Okay, sir. Thank you, sir.